Donc, vous me confirmez que vous voyez toujours bien les...
Parfait.
C'est
Très
parfait.
bien.
Donc c'est bon, Florence, tu peux commencer.
Voilà, donc aujourd'hui, nous avons le grand plaisir d'accueillir Chiara Ferrari, qu'on préférerait voir en chair et en os, mais bon, on la voit par Zoom, c'est déjà très bien. Donc Chiara, je la connais depuis très longtemps. Elle a fait sa thèse à l'Observatoire de Nice entre 2000 et 2003. Ensuite, elle a été postdoc Marie Curie à Innsbruck pendant 2 ans. Et puis ensuite, comme elle s'y plaisait sans doute, elle y est restée 3 ans de plus. Et puis, elle a obtenu un poste au CNAP, donc un poste d'astronome adjoint, qui ensuite est devenu un poste d'astronome. Elle travaille sur les amas de galaxies, donc elle a commencé par travailler en lumière visible avec des collaborateurs qui, eux, faisaient la partie rayons X. Et puis, elle s'est de plus en plus orientée vers les ondes radio dans les amas. Et depuis 2016, elle est directrice de SKA France. Donc, SKA, c'est le Square Kilometre Array dont elle va nous parler, qui est un énorme projet d'observation en radio avec des tas d'antennes, je ne sais pas combien, mais à la fin de son séminaire, je le saurai. Et donc, c'est un partenariat public-privé dont elle est la directrice et elle va nous parler de ce magnifique projet. Merci Chiara, et c'est à toi.
Merci beaucoup. And now I shift to English. It's a real pleasure. I would like to thank you for letting me talking about this project that is really, I'm very enthusiastic about. I have to say it's not just because I have to work on that. I'm really, I keep a strong enthusiasm despite the fact that I work a lot now for this project. So I'm really pleased to be able to talk about. And as I was discussing before the seminar with the other colleagues, I decided to give you, of course, an overview, even if not complete at all, about the science that can be done, but also about the development of this project, because I think that it's very exciting to be in the moment in which a new observatory is burning. So I decided to give you first a very short overview of what is the SKA, and then I will go into a little bit more details about how we arrived at the current phase of the observatory. I have to say that it's always, I've been giving a lot of talks via Zoom, of course, in this period, but I have to say that it's always very strange not to see faces of people. So please do not hesitate to ask questions even during the presentation if you wish. So the SKA is an ambitious international project to build and operate the world's largest radio telescope at low and mid frequencies. And as we will see, it will allow us to cover really a wide range of open questions of modern research in physics and cosmology. And this thanks to a unique combination of technical achievements, which and scientific achievements too. We will see that there has been a scientific development that has brought to the current design of the SKA telescope. And in most of the cases, these achievements did not exist a few dozens of years ago, when the embryo idea of what now is the SKA started to be conceived by a few visionary pioneers. I would like to stress that it was since the end of the 80s, more or less, that radio astronomers started to think about the SKA. And since its pre-1990 roots, radio astronomers realized immediately that to build such a huge telescope, Square Kilometre Array, means indeed a total surface of 1 kilometer, square kilometer. The project had to be global. It could not be a project just with a few one or a few countries. And so we often hear that the SKA is born global. And this is completely true because more than 15 countries have been working together within the coordination of the office of the SKA organization. We'll talk a little bit more about. And today, I'm very excited to say that the SKA is becoming a new intergovernmental organization for astronomy and for fundamental physics that is intended to last for 50 years and plus. And it's the second intergovernmental organization in astronomy after ESO. So I think that all this gives a clear flavor of how big it's this project. So to start answering immediately to the point raised by Florence, the SKA in its first phase, and today we talk about SKA 1, so what will be built. The rest, it's something that will be in the future, but really to be very concrete, let's talk about what is the SKA today. It will be an array of 200 dishes in South Africa and more than 130,000 antennas in Australia. So I hope, no, sorry, the animation is not working. Here it is. So why 2 telescopes? Because the lowest frequencies will be covered by these very simple small antennas grouped together in stations in hundreds of stations with hundreds of antennas per station. A station is the circle with the antennas that you can see here. And that will work in a similar way as the low-far radio telescope that is today operational in Europe, including France, or for instance, the MWA radio telescope in South Africa, in Australia. And this, as I said, will cover the lowest frequency part from 50 to 350 megahertz, and these stations will be in Australia, in the western part of Australia, very far from any kind of possible human interferences. While the more classical dishes used in radio astronomy since many years, many decades, will be built in South Africa, that is already hosting one of the SKA precursor, Mercat. We'll talk a little bit more about later on. And in total, we will have a bit less than 200 dishes that will cover the higher frequency part of the electromagnetic spectrum from 350 to 15 gigahertz, with some bands that are not yet financed in the current project of the telescope. So at the moment, the frequency coverage is not total from 350 to 15.4 gigahertz, but it's not too far, and the concept is already there to be built in the second stage. But what I would like to stress is that the SKA is known to be not only a radio telescope consisting of antennas. The computational part is extremely important because, as we will see, the SKA will produce terabits per second of raw data in each of the 2 telescopes. And this is a huge amount, and the computational part is extremely important. What we can achieve with the SKA, we have really to think that the computational part is the telescope in itself, is as important as the antennas to capture the light from the sky, because without that we cannot use the data from the antennas. So there will be 2 data computing centers, one in South Africa and one in Australia, to big data with hundreds of petaflop of required for dealing with the data processing. And the other very important part is a worldwide network of SKA regional centers that will be distributed all over the world, and that will be the place where astronomers can go and retrieve the archival data, but also do post-processing. So the 2 data computing centers are fully within the observatory, while the worldwide network of SKA regional centers are out of the perimeters of the observatory. They are, of course, an integrating part of that. But it's very important to stress that the idea is that we need to be able to use and reuse infrastructures for different kind of telescopes, and in order to make the best use of this kind of huge network of computational centers all over the world. And so it's a very interesting part of the work itself to build this network that can become really an example for this kind of applications. We will need more and more. The SKA is probably the biggest big data project at the moment, but we will need more and more. And building the concept of this network of regional centers is really an extremely interesting part of the work itself, in which we are devoting really a lot of time and work. And by the way, I hope to have the time to mention this at the end, but I already say that we managed to have a collaboration agreement signed between the SKA organization, CERN, PRACE and GEANT. So two big data projects and two big e-infrastructures at European level. This collaboration agreement is exactly intended to grow together towards something that will be needed for the whole community, and not only the scientific community, but also the societal, it will have also societal impact. So sometimes we hear about the SKA, yeah, it's interesting, but it will be sometimes in the future. That's not true. The SKA is now. The IGO basically exists, and the constructions will begin next year. And so I like to report the very nice declaration of Katrina Cesarski that you all know, I suppose, and that is the current chair of the SKA Board of Organization, that this is the culmination of many years of work by hundreds of people all around the world. And it's really, I think, a dream coming true for most of them. So how we arrived to this phase, I decided to give an overview, graphical overview of the development of the SKA project, of course, not including all the phases, but just the most important ones, dividing them in three parts. The first in blue represented the governance part, the green one in the middle concerns the technical development, and the red one in the bottom concerns the scientific development. So the history of the modern history of the SKA starts in 2012 with the creation of the SKA organization. That is a private company, a UK private company, whose objective is to design the SKA telescope and to then leave hands to something else, that is the IGO that I was mentioning. In 2013 and 2014, we had two very important steps. Concerning the technical part, there was the creation of, here you see 11 technological working groups, consortia. Each of those consortia was in charge of designing one part of the telescope, going from the antennas conception, the network, the computing part, and so on. And all this was, of course, coordinated by the SKA organization, but the effort was put by, as I said, more than 15 countries in the world to contribute to this kind of consortia. And in 2014, there was a big conference that was intended to starting to define more precisely what the SKA should look like, what so the technical choices need to be motivated, of course, by the scientific choices. And it was one of my first interactions, strong interactions with SKA, and I have to say that it's the moment in which I felt in love, if I can say like that, about this project, because I found this project extremely interesting. The SKA organization provided technical information to the scientific community, asking them, look, this is what we could build, what you can do with your science, what should we change, and so on and so forth. And there was this big meeting in which people were discussing together, and the science working, science book of the SKA came out from this conference. So when today you will see an author with the 2015, it's a paper coming out from this very important meeting. So going on from the governance and scientific point of view, first of all, the SKA organization realized that of course, the SKA observatory will be not an experiment project, it will be a huge observatory, and there will be key science projects that at the beginning of the operations in the first years will take from 50 to 75% of the observing time, because there are big domains that will be addressed by a big fraction of the community. So there was an initial definition of possible key science projects in 2015. And a very important step was in 2016 when the creation of the intergovernmental organization concept was launched in Rome. And as I said, this SKA organization is intended to provide the design of the telescope, but a bigger entity as to build and operate it. So 2018 and 2019, I selected to show the first two prototypes that were built. One of the Edition 10, was built firstly in China and then brought to South Africa, and then the first station of SKA1 Low. Between 2017 and 2019, sorry, there is a thunderstorm, so if you hear noise, it's due to that. There was the critical design review, first of the different elements of the telescope. So the consortia went through a very detailed critical design review process. And then in 2019, 1 year ago, exactly, because it was December, there was the system critical design review that went through very, very well. But 2019 can always be remembered, and I have to say that I had the pleasure to be present for the fact that 7 countries signed the convention for the creation of the intergovernmental organization. This was done in Rome at the Ministry of Education. And the first 7 countries that have signed the convention has been Australia, China, Italy, the Netherlands, Portugal, despite the fact that Portugal was not in the SKA organization, South Africa, and the UK. Now, these documents need to be ratified by Parliament. It's international, intergovernmental organization. It's not just a matter of one ministry deciding to go into a project. There is a long procedure to have these fully approved and integrated within each government. Again, this gives the size of the project. Today, 4 countries have already ratified the convention, that are the Netherlands, Italy, South Africa, and Australia. UK and Portugal are in a good way towards that. And in order to have the intergovernmental organization being operational, we need at least 5 ratifications, including the 3 host countries that are South Africa and Australia, of course, for the telescope, and the UK for the headquarters. So we are really very close to that phase. And indeed, what is now we know that will happen is that in the very early phases of 2021, the new observatory will definitely be born, with the first council meeting that is expected in January 2021. Again, all these to stress that the SKA is not in the far future, is very nearby future, is today basically. So why it can be today? Because a very important step related to the technical development was in September 2020, this year. Here you see the picture of the board. We had the very nice pictures of the board, but since I think it's already 3 times that we meet by Zoom. And it was a pity to be by Zoom, because it was an historical moment. The SKA board of the board of the SKA organization, approved endorsed the SKA1 construction proposal and the observatory establishment and delivery plan, because of course it's not only a matter of building the telescope, it has to be operated. And so these two documents are key, and they define the construction and operation of the telescopes, of the two telescopes of the observatory for the next 10 years. And so here you see a nice image, or artificial image of the telescope that will be in the future. But important to stress that this image is a composite image, the one that you see on the right. Sorry, it's difficult to the last one with all the antennas. It's a composite image because you can see some antennas that are real one. Those towards the center of the image are the Mercat antennas that will be integrated to the SKA1 mid telescope. And on the right side, sorry, you see the first prototype station of SKA1 low, and with all the others that will be built between 2021 and 2029. So I know it's a long time scales, and sometimes astronomers are scared about this long time scale. But what is nice to remember is that the SKA, the SKA is an array of antennas. So here you have a table with the 4 steps of 5 actually, because there will be an initial phase 0.5, during which defining the 4 phases of construction of the telescope. And little by little, astronomers can start to use the telescope, even if it's not fully completed, and it will soon become, I hope that my internet connection will not, I don't know if you hear, but there is really a strong thunderstorm here. So the astronomers can start to use the telescope earlier than when it will be finished. And how to prepare the use of astronomers of this telescope? The SKA organization keeps organizing the scientific meetings. One was in 2019. And there is another tool that is used by the SKA organization, that are data challenges. Here you have 2 images of the 2 that have been organized up to now. One in 2018. It consisted of a 2D image with the typical radio sources, star forming, galaxies, and AGNs. And astronomers had to run their source finding tools in order to evaluate the best one. And it has recently been launched, the second data challenge, that is completely open. And I think that there is still time to register. In any case, if someone has not registered and is interested, please let me know, and I can certainly discuss with the SKA organization for having you participating. The challenge this time is more challenging. The SKA organization has produced a cube of data. Here you see a zoom on a small part of the cube with the so it's a 3D image, right ascension, declination, and frequency, in order to look in particular for H1 emission from galaxies. And it's very interesting, this data challenge, not only because it will allow astronomers to test their tools, but because the data size starts to be big enough to also making tests about the future use of regional centers. Radio astronomers will not get the data on their laptops. They will have to work, as I said, on machines that are far away in these SKA regional centers. And this time, the SKA organization has asked to infrastructures, computing providers, to provide computing power and data storage in order to run the data challenge not in local PCs, but in large data centers. And I'm very happy to say that we discussed with Jansi. Jansi is following with interest the development of the SKA project, and the IDRIS, the Jansi GPU part of IDRIS will be is allocated, part of it, of course, not all of it, is allocated for the data challenge, and so persons that have developed tools on GPUs can will be able to use this facility. So it's a very interesting concept for mixing science and technological requirements together. So as I said, radio astronomers will be busy with the SKA, not only starting from the end of construction in 2029. Here you see some ideas of how the timeline of the SKA, scientific use of the SKA, will be developed. I have already talked about data challenges that are being developed, and what I would like to say is that I think that it's important that the community also discuss with the SKA organization in order to have data challenges that are of interest. I've been discussing recently with some colleagues in France. They would be very interested to develop data challenges, including foregrounds emission, diffuse emission. And I think that it's extremely important that the scientific community provide feedback to the SKA organization in order to have those data challenges that are of the greatest interest for them. So again, this is a call towards people. Please do not hesitate to discuss. I'm very happy to discuss with people in France if a message needs to be passed to the organization about the data challenges that you would like to have. The usual way, of course, is to register to the science working groups that are available in the SKA organization, and that are the places where people are discussing about the different scientific domains. Major science meetings, of course, started and will go on. Next one will be in April. By the way, if you want to register to the SKA France monthly bulletin, you will receive updates about all these kind of actions. And then, of course, there will be a different kind of essential steps toward the use of the scientific use of the telescope. The science commissioning, it's crucial, we know. I've been working for 10 years on the commissioning of LOFAR, and Robert Lang, that is a big expert who was working in ALMA, is now mostly leading this part of commissioning for the SKA. There will be early science projects starting from most likely 2026. So when the phase 2, do you remember, I go what year? Probably when AA2, so the second part of the telescope will be built, it will be possible to start with some early science. With shared risk proposals starting a little bit later on, and then PI proposals. But of course, as I said, key science projects will take a lot of the time of the telescope. And so it will be essential to keep organizing key science project workshops to put the community together, and then to prepare these big proposals. The important point is that all of them will require a lot of observing time, and so it will be important to find synergies and how to optimize the use of the telescope time. One question could be raised about participation to these proposals. Of course, there will be rules for participating to the SKA proposals, both in terms of key science project and PI. People from member countries will have the freedom, of course, to participate to those proposals with the certain rules that are starting to being fixed, but there will be then the IGO that will definitely decide how to do that. But there will be rules of percentage of contribution to the construction of the telescope and operation of the telescope versus allocated time per country. For non-member countries, just a few percentage of researchers can participate to some proposals based on their unique expertise, but of course it will be much more restricted. At a certain point, of course, SKA data will be open after a certain proprietary period. So what I often say is that I think that we already see the benefits of the SKA project, because really when we hear about a new golden age for astronomy after what was probably witnessed, I didn't, but in the 60s and 70s, that is often called as the golden age of astronomy. Now we are again witnessing really a golden age of astronomy, and thanks a lot to the SKA, because as I said, the SKA concept started in the late 80s, and since then astronomers and real astronomers have completely realized that they needed to prepare this telescope in terms of science, but also in terms of technology. And so there are a lot of telescopes that either have been built exactly in this framework. We build a new telescope and we acquire the knowledge, the know-how for building then the SKA, and are now by themselves very important telescope with very important discoveries. And I recall here LOFAR in Europe and Nénuphar in France, the LOFAR superstation, and this that is also operating as a standalone instrument, and is covering even lower frequencies compared to the SKA. So it will remain a unique telescope even when the SKA will be operational. And then there are telescopes like the JVLA that have already existed, but that have been recently upgraded. So you often hear about SKA pathfinders and precursors. Precursors are those telescopes that are built on the future SKA site, so in South Africa and in Australia. Pathfinders are those telescopes that have been built by countries that have are participating towards the SKA effort. And so, as I said, of course, it's very important to prepare the SKA, but they are very important projects by themselves. And so the first big impact of SKA has been to conceive this telescope. And I decided to start by showing some recent results that have been obtained through these some of these telescopes. I selected a few results from LOFAR, CHIME, and MEERKAT and ASCAP. And again, it's just a small overview, not at all what has been done in the last years. So here I decided to show to you two results that have been obtained on the left with MEERKAT and on the right with LOFAR. And they are related to diffuse emission and filaments at completely different scales, because on the left we see an image of our galaxy. By the way, many of these papers that I will show today have been published in Natural Science, and this gives you really a flavor of the impact that radio astronomy is having today in research. So as I said, on the left there is an image of a radio image of the central region of the Milky Way, and Haywood et al. have revealed a bipolar bubble structure. I don't know how to show. I hope that you can see these kind of hedge brightened lobes in the center of the image, very extended. They span 1 degree by 3 degrees. That means several hundred parsecs. And they extend above and below the galactic plane. And they are apparently associated with the galactic center. So many structures, many radio features appear in this image, including some bright filaments whose origin is still debated. These new edge brightened structures have been discovered thanks to the deep observations with Meerkat. So the two structures are edge brightened and are with a symmetry that imply a creation by an energetic event in the galactic center. And it has been estimated by Haywood et al. That the age of the two bubbles is a few million years, with a total energy of about 7 to 10 to the 52 ergs. And it has been postulated that the progenitor event has been an intense star formation event at the center of the galaxy a few million years ago, that could explain the increased cosmic ray density in the galactic center that was previously observed, and is the principal source of relativistic particles required, for instance, to power the synchrotron emission of the radio filaments that I was mentioning, and in the vicinity of the bubble cavities. So this image shows the power of having such a powerful radio telescope as Meerkat. And then on the right, you have an image of two galaxy clusters observed with LOFAR. So before commenting this image, I wanted to highlight that there is an ongoing LOFAR 2-meter sky survey that is a deep survey in between 120 and 168 megahertz that will cover the entire northern sky when it will be completed. And that is carried out with the high band antennas of LOFAR. So I would like to stress that because this survey is now becoming publicly available, and it's extremely deep. It's 0.1 millijansky per beam at a resolution of a few arcsecond. That is, this low frequency is really extremely important result. So researchers that are interested to look for that, they can go to the LOFAR 2-meter sky survey results. Because the first data release, year 1, covers already more than 400 square degrees and has been published in 2019. So this survey was expected to play an important role, for instance, for the statistical studies of diffuse cluster sources. So we know that merging clusters sometimes host diffuse radio emission, very weak, very diffuse radio emission, so very difficult to be detected because it's very low surface brightness. And until the advent of LOFAR, a few dozens of merging clusters were showing this kind of diffuse radio emission. But what I was saying when I had more time to work on this field was that I was expecting that with LOFAR and then with the SKA we could assist to the same kind of transition that we had in the 70s with the X-rays, that at the beginning of galaxy clusters were detected in X-rays just in a few cases, and then astronomers realized that the X-ray emission was always there. And now with LOFAR we start to see that radio emission is very frequent in galaxy clusters. With the first predictions that say that there could be diffuse radio emission showing the presence of cosmic electrons and weak magnetic fields in the volume between cluster galaxies in more than 70% of galaxy clusters, and possibly not only related to merging events. So it's really a new domain of research that exists since a few years, but now we can really start seeing galaxy clusters at radio wavelengths much more often and use this radio emission to get constraints about galaxy cluster physics. What I decided to show here is this very nice discovery, first discovery of a ridge of radio emission connecting two clusters that are Able 399 and Able 401. So the image that you can see the optical image of the two clusters, And this field was observed by LOFAR in depth at 140 megahertz, not by chance, but because these two clusters are nearby, and they have there's been a detection of X-ray emission, of course, in the two clusters, but Planck in particular detected signal between the two clusters. And indeed, LOFAR showed that there is radio emission too, that is most likely associated to a presence of old relativistic electrons, probably accelerated by previous active galactic nuclei phenomena that would not be visible, but are reaccelerated by weak shocks. And by weak, I mean Mach numbers of the order of 2 or 3. And so these relativistic electrons with the weak magnetic fields of the sub-micro-Gauss starts to re-emit at radio wavelengths, giving rise to this bridge of radio emission. This was expected, and it was nicely confirmed by LOFAR. Going on with some interesting radio results that shows how much radio astronomy is becoming not anymore a niche kind of research, but really a domain that is opening to the interest of many more astronomers, not just radio astronomers. I selected to talk about these two radio continuum surveys, one with MERCAT and the other with ASCAP. So on the left, there is a confusion limited image, deep image at 1.28 gigahertz obtained with the MERCAT within a field of view that is about 70 arc minutes with a few arc second resolution and with an extreme depth, because this goes to a sub-microjansky RMS noise. It's 0.55 microjansky per beam RMS noise. So what is extremely exciting here is really this. Before of course, radio surveys were used by radio astronomers, and astronomers working in optical or infrared were talking with the radio astronomers when they wanted to know something about AGN emission, radio emission from AGNs. But now, with this kind of depth, we are detecting the image is dominated by star-forming galaxies. And star-forming galaxies down to the early epoch in which we observed the burst of star formation in the universe. So the March and collaborators have shown that sources that are fainter than 100 microjansky are distant star-forming galaxies that obey the far infrared radio correlation, and sources that are stronger than 0.25 microjansky account for 93% of the radio background produced by star-forming galaxies. And for this deep image really has reached the depth necessary to reveal the majority of star formation history of the universe. And Mauch et al. Made an analysis and showed that a pure evolution of the 1.4 gigahertz local luminosity function consistent with the Maddow and Dickinson model for the evolution of star-forming galaxies based on UV and infrared data underpredicts their 1.4 gigahertz source count in a range from 10 to 100 microjansky. So we are really reaching the star-forming limits of galaxies in the universe, and this is extremely relevant not only for radio astronomers. On the right side, I show something that is an image that is somehow less exciting, but is extremely important, and the press has recently talked about this publication, because I show a table illustrating the summary of the rapid ASCAP continuum survey that is being conducted with the Australian Pathfinder ASKAP, Australian Square Kilometre Array Pathfinder, that is totally complementary with respect to MERCAT. MERCAT is able to reach very faint objects with a smaller field of view, so it's perfectly adapted to do deep observations, while ASKAP is has a much bigger field of view of 30 degrees and is extremely adapted to do rapid surveys. And this is shown by this survey, the RAX survey, that will provide a shallow model for future observations of the radio certain sky. And RAX is covering the whole sky visible from the ASKAP side. That means 83% of the entire sky, between 700 and 1100 megahertz. And this survey has mapped around 3 million galaxies in just 300 hours. And about, 3 million galaxies in just 300 hours. And about 1 million of those galaxies has not been seen before. So this means that rather than years of observations, these kind of new radio telescopes are allowing to discover, to open a new discovery space in just a few hundreds of hours. So here in this table, I've shown this table because it shows the comparison between the principal properties of radio surveys. So we know that one of the most used radio surveys in the history is NBSS, done with the VLA. And you can see here that in its final phase, that is indicated with the RAX-V, the sensitivity will be RAX-A, the first survey capacity, will be twice more sensitive than the NBSS with a better angular resolution. And this is just the shallow survey of ASKAP, done with a few hundreds hours of observations. So we reach already better sensitivity and resolution than what is done in years with the previous all-sky surveys. RAX is only the first step, as I said, is the first large area survey, shallow, and it will be used to get the first sky model for the observations of the southern sky, in particular for conducting EMU. That will be the deep ASKAP observations of the sky that will reach about 10 microjansky per beam RMS noise. And that will cover the entire southern sky plus the northern sky up to plus 30. So EMU may be compared again to the NVSS, except that it will be 40 times more sensitive and with 5 times more resolution. And here I show a first paper. So EMU is being developed. This deep ASKAP survey is being developed. And here I show just a recent result that has been published by the PI of EMU, Reionisation. And again, this is strongly discussed in the press about the discovery of circular radio objects. I see that I'm extremely slow, so I go quite quickly. I will give you the slides. You have several possible origin of this emission that at the moment they are not explained, this kind of circular radio objects that appeared and that have been discovered thanks to ASKAP. So being extremely late, I try to go very fast. I'm very sorry I spent too much time. So impossible not to talk about fast radio bursts. I wanted to talk more, but I cannot. So fast radio bursts have been discovered in 2007 by Lorimer on all data of parks, data of 2001. And after a very low detection rate of a few dozens until 2017, the SKA precursors and pathfinders, CHIMES and ASKAP in particular, have allowed to discover many more. We are now at several hundreds. Very interesting. Some of these fast radio bursts are repeaters, some are not. In the case of repeaters, it was easier to detect the hosting galaxy, because when they repeat, you know where you can go to look for the position. And it's something that happened in 2017 for the first host galaxy. And for the non-repeaters, ASCAP has been particularly useful, because ASCAP, basically, each single antenna of ASCAP look for a fast radio burst. And then if a fast radio burst is found, all the antennas of ASCAP work together in interferometry mode, and they observe a certain point of the sky, and they can have much higher resolution identifying the position of the radio burst. So to make a long story short, different physical origins have been proposed. Some of them are related to explosive events or merging of massive objects. Some theories are based on masers, mostly associated to repeaters. The fact of detecting the associated galaxies help, of course. The associated galaxies have different properties. In the case of non-repeaters, there are in general less star-forming galaxies than for repeaters. And very interestingly, there is the first claim of a fast radio burst associated to a galactic magnetar. What I would like also to stress again, to show that how radio astronomy is useful, these fast radio bursts are all not only important to understand what they are related to, so the physical origin, magnetars and or merging of compact objects, for instance, but because the dispersion measure of the signal as a function of frequency allows us to map the quantity of matter that they pass through. And so one important result that was obtained was that a fast radio burst traversing the halo of a galaxy showed that it was traversing much less mass that was expected. And an amazingly interesting result was obtained by Macquart et al. In 2020, because by using a small sample of fast radio burst with the detected galaxy, and so for which the redshift was known, Macquart and collaborators could measure the baryonic content of the universe, obtaining an incredibly good agreement with the cosmic microwave background and Big Bang nucleosynthesis. So this is the first probe, possible probe of such good agreement. Fast radio bursts have been shown to be extremely powerful tools to map the baryonic content of the universe. And this, I think, cannot be avoided, not only by radio astronomers, but for cosmology. And it's extremely interesting result. And I was very sad to hear that just a few weeks after the publication, this colleague died. So you can say, with all these discoveries, why building the SKA? And the reason is that the SKA will have an unprecedented image quality compared to current radio telescope, an unprecedented sensitivity and resolution. This is shown by these images comparing simulations of what can be observed with the SKA and with the JDLA. On the top right, you see the comparison of the sensitivity of the SKA compared to other telescopes. Please focus just on the blue curve for SKA1. And in particular, it's the survey speed. So the capacity of covering a huge region of the sky in depth that will be changed in an extremely important way. And so a plot that I like to show is this one, in which you have on the x-axis the sensitivity limit of surveys, and on the y-axis the surface of the area that is covered. And so you can see the pre-2010 surveys, either deep surveys but on small fields, or wide surveys but not sensitive, not very sensitive. We have seen that with the SKA precursors, we are sensibly changing this. We start to have very good and deep wide surveys, but the SKA will completely change our view of the radio sky, because we will go in higher depth compared to current deep surveys within the whole sky. So can you imagine the discovery space? And this discovery space will be allowed also to be opened by different kind of observing modes of the SKA, very flexible. So you can do images, you can do transient search through tide array beams. And I don't have the time to enter in detail, sorry, but again, you will have the slides, and anybody that's interested to know the different observing modes. So what I wanted to stress is that the fact of having so many different ways of observing the sky will of course increase the discovery space. So the SKA is expected to cover a wide range of science, really going from cosmology to the planetary discoveries. Can I talk 10 minutes more? I will go very quickly, but can I have 10 minutes more?
Maybe 5, is that possible?
Okay. So I will go very, very quickly then. I will just show you the slides. So what I will show the slides are about the fields in which the SKA will be a unique instrument. One will be for galaxy evolution, the study of H1 hydrogen is the reason why the SKA was started to be conceived. We will see we can go very far in time, detecting the H1 content of galaxies in the period in which we have seen a transformation in the star formation rate of galaxies. And what I wanted to stress, and I've shown before, through radio continuum images, we can also have an independent and biased, dust unbiased way of measuring star formation rate. So here it's a current study, recent study of H1 content of galaxies with the VLA. We arrived at a redshift about 0.2 on this kind of small surveys. This is the quantity of H1 gas measured as a function of redshift in this JVLA typical survey on 0.25 degrees field. And here is what is expected to be done with the SKA. It's exactly the same kind of plot, H1 mass versus redshift that can be sampled. The black rectangle shows exactly the same region, showing small inset, but you can see that from a few tens of galaxies, we will go to hundreds and thousands of galaxies for which we can detect H1 up to redshift more than one. H1 hydrogen, I cannot not talk about the epoch of reionization. As you most likely know, we will be able to detect the H1 in contrast with respect to the cosmic microwave background signal. So I unfortunately will not have the time to enter in detail about that, but basically the contrast will be either positive or negative. So we will see the H1 as a negative contrast with respect to the CMB or a positive one. But basically what the SKA will be able to do is to image the epoch in which all the structures of the universe started to form before the first light was emitted, getting a direct image between redshift 6 and 12, and power spectrum up to redshift 25. So we will really have, for the first time, the possibility to study the epoch of reionization and the cosmic dawn. And then there is, of course, cosmic magnetism. The synchrotron radiation is an excellent way of studying magnetic fields in the universe. One of the most powerful tools is through Faraday rotation. We will, so basically when sources in the background radio sources in the background traverse a magnetized plasma, you can measure the magnetic field in between the radio source and the telescope. And so in order to measure, map magnetic fields in the universe, you need to have a lot of sources of a background. in such a way to be able to measure magnetic fields in many different regions of the sky. And the SKA will provide us 300 times more extragalactic rotation measures. That means that we will be able to measure magnetic fields in many more details all over the universe. And of course, extremely important pulsars. Pulsars are important by themselves for doing astrophysics studies for the evolution of stars, but also test of gravitational theories. But pulsars in particular are extremely powerful tool to measure nanohertz gravitational waves. So we know that there are already pulsar timing arrays operating to look for these nanohertz gravitational waves associated to supermassive black hole binaries and mergers and primordial gravitational waves. The SKA will increase, as you can see on the bottom right, enormously the quantities of pulsars that can be used for pulsar timing arrays and the sensitivity. So we will have the possibility, most likely, to detect the first nanohertz gravitational waves. And of course, there will be a lot of synergies with many other major facilities in most of the fields of cosmology and astrophysics. This is well known by the French community. I really go very quickly. We published in 2017 the SKA French White Book, and with about 180 researchers, both from research institutes and private companies. And what I would like to stress is that we had the richest synergy chapter ever published in any SKA white paper book, even in the big one published by the SKA itself. So very quickly about the SKA in France. In 2016, the SKA France coordination was formed. At the beginning, was just a coordination that started by CNRS INSU with research institutions. In 2017, as I said, we wrote this white paper book, and we had a lot of interactions, not only with researchers, but also with industry. So in 2019, the Maison SKA France was formed with the academic partners, but also at the time several industries participating to Maison SKA France and contributing to Maison SKA France. The same year in May, the ministry published the new the large research infrastructure roadmap, in which SKA was inserted as a project. That means it was not financed, but was labeled as an interesting project for France. And through the funds raised from Maison SKA France and this SKA project as a project in the ministry roadmap, in July 2018, CNRS became the new member of the SKA organization. And you see me in this image very smiling because it has been really major achievements. In November of last year, we had 2 new academic members, Diffuse for CEA and INRIA. So as you can see, for instance, from the participation of INRIA, is not only interesting researchers in astronomy. We have a lot of discussions about the technical contributions with companies, and at the moment we are extremely strongly positioned to have an important participation to the SKA telescope for the computing part, in particular for the 2 centers that will be in South Africa and in Australia. Of course, all this depends on the decision of the SKA or the position of France in the SKA that is currently under evaluation with a strong support from CNRS. So if France will enter in the SKA observatory is being discussed. I don't have the time at all to enter in these details, but let me just finish, and probably I just go to this slide, by saying that the reason why there is so strong motivation behind the SKA. It's not only for the huge quantity of physics and astrophysics that can be done, but because it's a planetary project. That means that is really helpful in creating collaborations, and because there are a lot of actions with the schools, students at all levels, from children to graduate and undergraduate students, and this is particularly important not only for South Africa but for all Africa. There are really a lot of actions. I will give you the details. I will provide you the slides you can look for, and there are really a lot of actions. This is extremely important, in particular because in Africa, Mercat is a good example. They built their own telescope, they are operating that, and the idea is to have countries not just using other people in other continents, but teach them, and having the SKA used as a tool for improving society. And I really trust in that. We presented this in a session that was organized during the General Assembly this year, and there is really a strong contribution. One is, of course, also related to the green energy, because we are perfectly aware that with the data rate of the SKA, we need to develop clever ways of using compute energy for computing, and all this goes towards the green revolution, of course. And we are working with French companies and partners all over the world on this topic. And I stop here. Thank you.
Thank you very much, Chiara. That was a very, very exciting project, and we all look forward to all these incredible data. So I see questions. So Marta first.
Thank you. So yes, first I agree with Florence. It's fantastic, and also the very last slide that you had was very important. So not only for scientific reasons. So I have a curiosity about the circular radio objects that you showed.
Yeah, I probably share again the screen.
Yes. So there is really, they could be either galactic or extragalactic. So there is no measurement of the redshift or any multi-wavelength observation support.
The only thing that, sorry, I'm looking for a slide. The only, they compared, of course, with the multi-wavelength data. In particular with the WISE and I think with the DES survey. There are no redshifts. So just in one of the cases, the one named ORC4, there is a central object at the very center. You can see that is also bright in radio. And in the other cases, and also in the ORC1, there is a possible central object. But it's not, I don't think there is not redshift. And in particular, for ORC4, I would say that is probably the easier to be associated to this central object, but the others are not really. And it could be indeed galactic because they are quite big. They are 1 arcminute diameter. And it's the reason why some of the possible reasons were excluded. But by combining all the information, spectral index size and so on, at the moment they did not find any possible explanation. But what I wanted to show this because I think that I would like the more astronomers look at these kind of things and think on their side. And it would be great if there is a bigger community looking for ideas for that.
Thank you. I love mysteries as well.
Do they have a counterpart in any other wavelength? No.
No. That's because at the beginning, indeed, they were thinking, for instance, that could be associated to ring galaxy or star-forming galaxies, but there is no optical association, and then the explanation is unlikely.
Okay. So Hervé Dole?
Hello, Chiara. Hello.
Bonjour.
Good talk. Exciting stuff. I was not attending the whole time, so my apologies if you said it already. On slide 17, you mentioned all the surveys, and I'm more familiar these days with LOFAR, the LOTS survey at 2 meters, which is completely amazing. And 17 plutôt. And so you show here the different surveys at 1.4 gigahertz, so 21 centimeters. So
yeah,
you can see LOFA because it's not the same wavelength, but
yeah.
you mentioned earlier in your talk that now we are able to see star-forming galaxies at some reasonable redshift. At the difference of ancient times where radio were only used for AGNs and stuff. So it's really exciting for infrared people like me. And so how would you compare the, this 21 centimeter sensitivity and stuff with other wavelengths? Because now this new field opens. So is it comparable? Is it better to observe at 2 meters or 21 centimeters? So what's the situation?
So this plot exists also at low frequencies because it's a very pertinent comment. It's in a paper of Tingay et al. I don't remember the year now, but basically the situation at low frequencies is the same. So with the kind of contribution expected in terms of frequency coverage and depth for at low frequencies. I think that at low frequencies, you can separate better the two components of the radio emission associated to star-forming galaxies, in the sense that at these higher frequencies, you still have a mix of synchrotron and free emission. While at lower frequencies, you basically isolate the synchrotron radiation. And I remember that I made this comment several years ago, but I still think that if you are able to isolate the physical process behind the emission that you detect, it's always worth in order to interpret why you can observe a change in the star formation rate of galaxies. So if I have to be honest, I of course I'm expecting a lot from these high frequency observations, but still I think that lowest frequencies are going to provide very good important in terms of not only detecting the star formation rate, but also characterizing its physical origin.
Okay, thank you. More questions? I don't see any more hands.
I'm very sorry that I went very fast on very, very interesting